All right, so now I present the second derivative test. So let's suppose that the second order partial derivatives of f are continuous on a disk centered at the point P, and assume that P is a critical point of f where the gradient vanishes. That is, the gradient at P. Gradient of f at P is the zero vector. And I would like you to recall at this point the second order derivative of f. So let me go back. Yeah, the second order derivative of f is this 2 by 2 matrix right here, and the discriminant is the determinant of this 2 by 2 matrix. So basically what we are trying to do is that we have this critical point and we want to know whether at this critical point we have a local max, local mean, or neither, a saddle point. And so it turns out that if the determinant of the second derivative of f at p, which is the same as the discriminant, if the discriminant is positive and the second order partial derivative of f with respect to x twice at p is positive, then f of p is a local minimum. If the discriminant is positive and the fxx at p is negative, then f of p is a local max. If the discriminant is negative, then f of p is neither a local max nor a local mean, in which case p is a saddle point. Okay, so that's the second derivative test, and let's apply that in the following example. So let's say that I have the function f of xy equal to x to the 4 plus y to the 4 minus 4xy plus 1, and I want to find the local max and local mean values of f, if any, and also the saddle points of f. So the first thing we want to do is we want to find the critical points, which we have actually done in a previous example. So to find the critical points, we simultaneously solve these two equations, that fx is 0 and fy is 0. Now fx here would be 4x cubed minus 4y, and fy would be 4y cubed minus 4x. And previously, like I said, in an example, we solved this system of equations and we got three critical points: 0, 0, -1, -1, and 1, 1. So we have three critical points, and now we apply the second derivative test to each of these critical points and see if we have a local max or a local mean or neither at each one of the critical points. So the second order, the second derivative of f at xy is this 2 by 2 matrix, and in this case it's gonna turn out it is fxx is 12x squared, fyy is 12y squared, fxy is -4, fyx is -4. And again, we have actually computed this in a previous example. Now notice that let's pick the critical point 0, 0. So at the critical point 0, 0, what is fxx? Well, fxx is this quantity right here, and at 0, 0 it is 0. So fxx is 0, and if you look at the second derivative of f at 0, 0, well, it'll be so x is 0, y is 0, so you get 0, 0, -4, -4. And so if you look at the determinant of that, or that means that you're looking at the discriminant here, it is equal to -16, which is negative. Now the fact that the discriminant is negative, it means that at 0, 0 we have a saddle point. Okay, so now we look at fx. We look at the discriminant at -1, -1, that is, we look at the determinant of the second derivative at -1, -1. So right here, we plug in -1 for x and -1 for y. If we do that, we get 12, -4, -4, 12. And if you take the determinant here, that's going to be 144 minus 16, which is positive. Now the discriminant is positive, so what is fxx evaluated at -1, -1? Well, fxx is this quantity right here, and at -1, -1, it is just positive. So fxx is positive, the discriminant is positive, so at this point, -1, -1, we have a local minimum. Similarly, if you calculate the fxx at 1, 1, that was the last critical point, we will get 12, which is positive, and the discriminant evaluated at 1, 1, that is the determinant of the second derivative at 1, 1, it is 12, -4, -4, 12, which is also positive, so we have a local minimum at 1, 1 as well. Okay, so I will stop the video here. So this is going to be end of my discussion on the second derivative test. In the next video, we will be looking at the extreme value theorem.